Geometry, lesson 14, we're going to be talking about disproving conjectures with counterexamples. We've already kind of talked about this because what we've done is we've talked about conditional statements, if hypothesis, then conclusion. The counterexample is if the hypothesis is true, then but the conclusion is not true. Are you awake? You okay this morning? Okay. All right, so if we have a conjecture that is if two lines are both intersected by a transversal, then they are parallel. That's a conditional statement, but if I can come up with a counterexample, then it's not true, right? Or not necessarily true. So this conjecture that is given here is actually false because it's not necessarily true. Now, it's sometimes true, but two lines do not have to be parallel to be intersected by a transversal. A simple way to prove that this statement is not true is to use a counterexample. In this case, a counterexample, well, used to exist, and I don't know, I must have lost it at some point. All right, would be, here's a line that's not parallel to that line. Is it on the next slide? Did it get moved over? Okay. Well, in any case, there's a counterexample. Okay? Here's two lines that are not parallel, but they are intersected by a transversal. Okay? So two lines intersected by a transversal don't have to be parallel. Okay, there they are. Okay? So in order for us to have a counterexample, I have to meet the hypothesis but prove that the conclusion is not necessarily always true, right? And by, I've used the example over time, different things, but, for instance, if we use a real simple one like if an animal has 4 legs, then it is a horse, right? What's a good counterexample to that? Is a flamingo a good counterexample? Why not? Because a flamingo only has 2 legs, which means it doesn't meet the hypothesis, right? A cow is a good example because it has 4 legs, but it isn't a horse, right? Okay. All right. So that's what we're looking at. And you can look at that definition there. Not all conjectures, not everything that we're going to look at has to be geometry, okay? For instance, 4 legs and a horse. Counterexamples can be used to disprove algebraic conjectures or any other kind of conjecture for that matter. All right, which brings us into lesson 15, which isn't necessarily even like lesson 14. Okay, that's just kind of how Saxon does some things. We're going to talk about polygons. We had an introduction to triangles the other day. Today we're going to talk about polygons. A polygon is a closed plane figure formed by 3 or more line segments. Okay, line segments. Which means all of my sides are going to be straight. Okay, each segment intersects exactly 2 other segments only at their endpoints, so there's no overlap, there's nothing excess outside of it, it's all closed. All right, no 2 segments with a common endpoint are collinear, okay, which means we're not using an endpoint and then going on to make a longer line for some reason. Okay, the segments that form a polygon are called sides. A vertex of a polygon is the intersection of those 2 sides. You understand all that. But here's some examples of polygons, and here's some examples over here to the right of non-polygons. Okay, you'll notice that we have curves, okay, which means we're not using segments. Okay, we also have an open figure. Okay, right here is probably one of the better examples, because it's just not closed. All right. Equal angular polygons, equa meaning equal, angle meaning angle, so equal angles, which means all the interior angles of that polygon are congruent to each other. Okay. And equilateral, equa meaning equal, lateral meaning side, right? Those of you guys that are in sports, you should know what the term lateral means, right? You guys probably use it more in the real world than, actually it doesn't mean backwards. It could mean backwards. It just means to the side, right? A lateral pass is a lot of times to the side. Okay, so lateral meaning side. Equilateral means equal sides in which all sides are congruent. If a polygon is both of those things, equiangular and equilateral, it has to be both. It can't be one or the other. It's got to be both of those things at the same time. If it is both of those things, equilateral and equiangular, we call it a regular polygon. Okay? Okay? So they're going to ask you a question later on. They're going to say, show you a picture and say, is this a regular polygon? And if they only show you one of those two things, you're going to say, no, I don't have enough information. We've got to be able to prove both of those things to say that it's regular. Does that make sense? All right, if a polygon is not equiangular and it's not equilateral, meaning it's neither of those two things, then we refer to it as irregular. Okay? All right, let's try to make an example of an irregular polygon. Okay, something like that. All the angles aren't equal. All the sides aren't equal. It is a polygon. It's made up of line segments that connect at endpoints, but that's all it is. So that's what we would call an irregular polygon. Let's see. Another one that maybe looks a little bit more regular but isn't considered regular is, oh gosh. And I can't do a very good job of it, but if there was a really good drawn star here, let's see, I think I can actually maybe even pull one up. Let's see, let's try this. Yeah, you would think that's not a regular polygon. Okay, that's irregular. Okay, because it's not equiangular, and it's, well, I guess it might not be considered irregular because in this case, all of the line segments might be congruent. All right, so we're going to talk about classifications. Now, in your book, you have a more extensive chart. It goes on out and shows you irregular polygons on page 90. We'll show you some examples of irregular polygons. And lo and behold, I wasn't too far off. If you look at a dodecagon, it kind of looks a little bit like our star. So we all know what a triangle is. Okay, it's got three sides. We know what a quadrilateral is. That's actually the more correct term than just saying like square or rectangle if it has four sides. We call it a quadrilateral until we have more information. Then we have pentagon, right? Hexagon, heptagon, octagon, nonagon, decagon, hendecagon, and dodecagon. Okay. And does anybody notice what tends to happen to the regular polygon as it increases in number of sides? What does it begin to start to look like? Begins to start to look like a circle, right? In fact, based upon like computer images, right? Any of you guys play whether it's computer games or video games? Anybody? Okay, somewhat. All right. So one of the things that they do to make graphics in video games is that obviously there's really no curves, but the more sides that we apply to it, right? The smaller the pixels get, right? The pixels have a definite size. And the smaller that they get and the more of them that we can include, even though this dodecagon is not a circle, the more sides I start to add to it, the more I can start to show curvature, right? So that's as you see graphics in games and videos and those things, computer-generated images start to get better. What they've been able to do is increase the number of pixels, which is able to cheat the idea of a curve, even though basically all you're doing is you're adding more and more line segments, and they're just making them smaller. Does that kind of make sense? I think it's kind of neat. But anyway, obviously we can create polygons with more than 12 sides. So what do we call like something with 13 sides? Or anything more than 12? Right. We use the number, right? So let's say 44. Something with 44 sides we're going to say is a 14-agon. Or 44-agon, sorry. Okay? So anything more than 12 has just the name of the number, agon, on it. All right. All right, we've got a little bit more here in terms of classifying some things. One of the things that we want to pay attention to are diagonals. A diagonal of a polygon is a segment that connects two non-consecutive vertices of a polygon. If I go back a page, okay, a diagonal would go from there to there. I can draw one from there to there, here to here, those types of things. But that's, and I can make some more in there, but that's what we're kind of looking at, is going from non-consecutive vertices. Okay? Diagonals can help determine whether a polygon is concave or convex. A convex polygon, every diagonal of the polygon is inside of it. Just like whenever we look at this little picture we drew over here, where I have my diagonals, all those diagonals are inside that polygon. Okay, but if I go back to an earlier picture, right, you'll notice that if I go from this point to this vertex over here, now I have a diagonal that is outside the polygon. Okay, so we have a different term. Anytime a diagonal, or drawing from one point to another point on a polygon, anytime that line shows up outside of it, it is concave. Okay, so you need to know the difference between convex and concave. My star over here, okay, is it convex or concave? Either one. I'll give you a hint. The answer to them, the answer is the same for both of them. Are these convex or concave polygons? Convex means that all their diagonals are going to be inside the polygon, right? Concave? Okay, that's the wrong one. It's the one I didn't say, right? Because I can draw a point from that vertex to that vertex, and it's going to show up outside the polygon. So that's my test. Okay? Just the same way, if we want to test and see if a graph is a function, we'd use a vertical line test. If I can draw a line from one point to another point, and that line shows up outside that polygon, it is concave. It's easier, for me, it's easier to think about the term concave than it is to understand convex. All right? Concave, the second syllable is what? Cave. Right? It caves in. Right? Right? So there's a dip in it somewhere. Okay? Does that help? Right? I think of a cave, a big overarching rock, and if you go inside of it, it dips in. Okay, so concave. Hopefully we understand that. Okay, so that's the difference. In a concave polygon, at least one diagonal can be drawn so that part of the diagonal contains points in the exterior of the polygon. If two polygons have the same size and shape, this is information we already know, but we know that they're congruent polygons. Same size, same shape. Okay? And then finally, I think that this is the end of this, so there might be another slide. But we're talking about interior and exterior angles of polygons. An interior angle, this is an easy one. It's inside the polygon, right? We've got a closed geometric figure. Any angle that occurs inside of it is considered to be an interior angle. But then we have exterior. And an exterior angle is not, this angle right here, okay? It's if we took a side and continued it on out, right, it would be the angle formed between that extended line and a consecutive side to that. Does that make sense? All right, so, if we were to do all of these, right, look, those angles would look like this. And you guys, a couple of you who are in Algebra 3 have seen this, right? We've talked about exterior angles, right, and how to find those. Okay. All right, so that's the end of that slide. Let me pull up some questions that we can answer for about the next 9 minutes before I let you guys get started on your stuff. Okay, like I said, do we understand why we're doing two lessons? Because one is counterexamples, which is fairly easy to do, and the other one is shapes, right? So I felt like that was Easy enough information. We're about a day behind where we wanted to be as it was, and so this is going to get us back to where we want to be. Question number 1. This is actually, more students struggle with this question than I kind of thought would. But it says, show that the conjecture is false by finding a counterexample. Keep this in mind. The first thing that I need is I need the hypothesis to be true. So I need to pick an option that is true to A is greater than B. All right. So look at A. Is 11 greater than negative 3? Okay. B. Is 11 greater than 3? Yes. On C. Is 3 greater than 11? Okay, so I can throw out that as an option. D, is negative 11 greater than 3? No. All right, so that brings me down to 2 options. All right, now I have to go and I have to find the one that is not true in this area right here. Okay, I need it to not be true in order for it to be a counterexample. And that's something that I think that we struggle with, is I need to find something that is wrong in order to be right. Okay? All right, so when I divide A over B, I need it to be less than 0. Is 11 divided by negative 3 less than 0? Yes or no? What do you think, Jordan? Well, I mean, you're looking at the question. You look like you're putting it together. Is 11 divided by negative 3 less than 0? Is it? Okay. Now, is 11 divided by 3 less than 0? No, right? It's going to be a positive number. So my answer is A. That's my counterexample. It was true by the hypothesis, but it didn't meet the conclusion. Okay, therefore it's a counterexample. Okay. All right, move on down here a little bit. All right, another counterexample. It says, if possible, use the data table to prove the conjecture is false. This says, if an element is a metal, then it's solid at 70 degrees Fahrenheit. All right, what they're saying is, okay, something is solid until it melts, correctly? Correct? Correctly, yeah. Something is solid until it melts. Okay, so tungsten doesn't melt till 6,192 degrees. Is it solid at 70 degrees? Yeah, so that's not a very good counterexample, is it? Okay, and we would see that true with copper and silver. Both of those are solidly still solid at 70 degrees, but mercury melts at negative 38 degrees Fahrenheit. So is it solid at 70 degrees Fahrenheit? No. It's already turned to liquid, right? It turned to liquid a long time ago. So D is your answer. Okay? All right, now let's get into some shapes. All right, number 3, is that regular or irregular? We should be pretty quick about some of these. Regular or irregular on 3? Irregular, good. Is it convex or concave? Concave. Look. Cave. Caves in, right? Goes in. Here's a diagonal, and it falls outside the figure. Okay. So irregular, concave. Let's look at number 4. Now, they're not asking convex, concave, regular, or irregular. They just want to know, what are we going to call this? Well, how do I go about figuring that out? Count the sides. Best way to do that is use tick marks to keep track. It's 2, 3, 4, 5, 6, 7, 8, 9. What do we call a 9-sided figure? A nonagon. Good. Okay. Let's see. I don't know. Let's go to number 6. I feel like maybe that's... is that regular or irregular? 6. Irregular. All right. How many sides does it have? Is it 6? All right, so what do we call a 6-sided figure? Hexagon. So D is my answer, right? I think number 5, it is a polygon, and it's got 10 sides, so it's going to make it a decagon. Okay. All right, this is talking about congruent figures. All right, it says that they're congruent. If I don't know what this side is, what should it be? Should be 15. All the other corresponding sides are congruent, so therefore I'm just going to look at 15. No math involved there. It's pretty easy. Okay. 8. Which of the following is a counterexample to the following conjecture? If x squared equals 25, then x equals 5. This is another one that I've seen students struggle with. Okay, remember it's got to meet the hypothesis, correct? So if x equals 25, is 25 squared 25? No. All right, so that doesn't work, right? We've got to meet the hypothesis first. All right? All right, negative 5. Is negative 5 squared 25? Yeah. Is negative 5 equal to 5? No, so that's my counterexample. Okay? So you got to remember, if they start giving you questions that involve like a square, right, negative is also an option. Okay, they'll try to trip you up there. Negative 5 times negative 5 is 25. The problem there is if they did like negative x squared, right? Because, and then, x was negative 5, right? So what we would have is this, right? So that would be 25, and then it would end up being negative 25. Okay? All right, let's look at one more counterexample. Number 9, which is a counterexample to the conjecture. It's got to be less than 9, but it's whenever I square it, I get something greater than 81. Okay, we would agree that negative 7 is less than 9, right? What do I get when I square negative 7? 49. So that doesn't work, right? Because I'm still less than 81. What about negative 12? Is negative 12 less than 9? Yeah. What do I get whenever I square negative 12? Is that less than 81? Is that a counterexample? Yes. Okay, again, an area where squares give you a whole different possibility. Okay? All right, do we feel like we're on pretty good ground there? We understand counterexamples, we understand our shapes? Okay. I'll let you guys go from there.